In this lesson, we will derive the principles that will enable us to describe what molecules look like in 3 dimensions. In other words, their molecular geometries. The basic principle that underlies all of this is known as VSEPR theory. VSEPR stands for valence shell electron pair repulsion. Okay, valence electrons, of course, are the outermost electrons around an atom, and what VSEPR theory states is that the electrons around an atom, whether they are located in bonds or in lone pairs, want to be as far away from each other as possible. And that should make perfect sense to you because electrons are negatively charged and they don't like each other very much. Negative-like charged objects repel, so electrons that are negatively charged are going to repel other electrons that are also negatively charged. Okay, so how do we put this theory into practice? Well, let's consider the simplest organic molecule, and that's methane, with molecular formula CH4. All of the electrons around the central carbon atom in this case are located in bonds, and furthermore, they're all located in single bonds, and there are 4 carbon-hydrogen single bonds. So what are some possible geometries for methane? Well, the one that may come to mind first would be what's called square planar geometry, where you have the carbon atom at the center, and then you simply have 4 hydrogen atoms around the carbon pointing towards north, south, east, and west on a compass, for example. In this case, all 5 atoms will lie in the same plane, and there would be a 90-degree hydrogen-carbon-hydrogen bond angle present in this molecule. That may seem like you're getting the electrons as far away from each other as possible, but it's actually not correct. The reason being that the square planar structure limits you to 2 dimensions. If we make use of the 3rd dimension, we can actually get the electrons in the CH bonds even further away from each other. And the geometry that's actually correct for methane is what we call tetrahedral geometry. In this case, the hydrogen-carbon-hydrogen bond angles are increased up to 109.5 degrees. We only have 3 atoms lying in a plane, and one of the hydrogen atoms is lying in front of the plane defined by the other 3 atoms. The other hydrogen atom is lying behind the plane defined as by the first 3 hydrogen-carbon-hydrogen atoms. Okay, so we're now using all 3 dimensions, and it allows our bond angle to be bigger, meaning that those electrons actually get further away from each other. In order to be able to depict this 3-dimensional object on a 2-dimensional surface, like a piece of paper, a blackboard, or a computer screen, we've had to develop a convention to show which of these hydrogens is coming out towards you and which of these hydrogens is going back away from you. Okay, so the wedge, the dark wedge, indicates that an atom is coming out towards you, and the dashes indicate that the atom is going back away from you into the page or into the screen, as the case may be. You need to be completely familiar with this notation and to always use it consistently. There will be problems that show up later in the course that you have to clearly indicate whether a hydrogen atom or some other atom is coming out towards you or going back away from you. It doesn't matter how you draw the molecule. If you put that wedge in, that's always going to mean coming towards you. If you put those dashes in, it always means going back away from you. Okay, so tetrahedral turns out to be the correct structure for methane, in which all we have are single bonds. Now, what happens if we incorporate functional groups that contain double bonds? Let's consider ethylene. Okay, C2H4, and that's a molecule in which you have a carbon-carbon double bond. In this case, we can get the hydrogen-carbon-carbon angle up to 120 degrees, keeping everything in the same plane. Why is that? Well, around the carbon atom, you have a total of 360 degrees in a circle going around that carbon atom. And when there are 3 other groups bound to that carbon, we can get them 120 degrees apart without having to go outside of the plane. So it turns out that this geometry is what we call trigonal planar. It is a planar structure, and there are 3 things bound to each carbon atom. Finally, in molecules that contain a triple bond, in alkynes, the molecule is going to look something like this. You've got the triple bond between the central 2 carbon atoms, but the hydrogen-carbon-carbon bond angle is now 180 degrees, and as you can see, this molecule is completely linear. Okay, so that's what its geometry is, and 180 degrees is its bond.